Hello, my dear students. Welcome into the second lecture on high performance thin layer chromatography. In previous lecture, we have seen introduction and principle of the HPTLC. In this lecture, we are going to learn sequence of steps in operation of HPTLC. That means when we operate the HPTLC instrument, what will be the step we have to follow that we are going to learn into this lecture. Actually, the first component into this HPTLC instrument, the selection of HPTLC plates or pre-coated plates and sorbent. That means what type of plate, what will be the size of that plate, and pre-coated plate along with sorbent material. That means what type of material will be used for making the pre-coated TLC plate. The pre-coated plates with different support material like glass, alumina and plastic will be used. C. Supporting material in pre-coated TLC plate, generally glass, alumina and plastic material will be used. The stationary phase for prepare HPTLC plates are silica powder, aluminum oxide, cellulose, polyamide, silica gel, etc. See, this is the material. By using that material, we can prepare the stationary phase of the high performance thin layer chromatography plates. These material will be coated on supporting material to form HPTLC plate. That means above material. That means silica powder, aluminum oxide, cellulose, polyamide, silica gel. That material will be coated on what? Supporting material to form what? HPTLC plate. So then the TLC plate with sorbent thickness is 1 to 2 mm are used for qualitative and quantitative analysis. See, that means this sorbent thickness on the TLC plate that should be 1 to 2 mm only, not more than that. Usually, HPTLC plates with sorbent thickness is 100 to 250 micrometer. Sorbent thickness is around. In case of HPTLC, that will be 100 to 250 micrometer. This is the thickness of the sorbent material on high performance thin layer chromatography plate. Now we will see the second criteria of this. Pre-coated plates are available in size of 20 by 20 centimeter or either 10 by 10 centimeter with aluminum or polyester support. See, this 20 by 20 centimeter size, that actually available size, but whatever our requirement, according to that we can cut that plate according to our requirement with the help of scissor or say blade. These plates can be cut to size and shape for use particular analysis by using scissors. Depends upon the requirement. We have to cut that plate into the particular size and shape. Freshly opened box of HPTLC plate usually not required to activation. See, in previous lecture we have seen activation part of the HPTLC plate. Suppose the plate will be contaminated by some impurity, or you can say by due to the humidity, that plate should be activated, then we can use that plate into for what we can say analysis of the sample material. Suppose plate exposed to humidity or kept on hand for long time may have to activate by placing in oven at 1110 to 120 degree Celsius for 30 minutes. Suppose our fingerprint will be observed on that when we handle that plate, when we observe the fingerprint on that plate, at that time we have to activate the plate into the oven at about 110 and 120 degrees Celsius for 30 minutes to, to avoid the contamination into the separation of the sample component. Then keep that plate in washing chamber in vertical position. After the plates are removed from washing chamber, they should always be dried in vertical position. See, when we wash that plate should keep in vertical position for drying purpose. When we keep horizontal in any particular surface, at that time maybe that washing solvent may be stuck into the plate. That's why we have to keep that plate in vertical position. Now the second component, or you can say second step, that will be the sample preparation. Here we have select the TSC plate according to the size, what will be the sorbent material we have seen. Now the second step into the HPTLC operation, that is sample preparation. Sample pre-treatment is necessary such as sampling, mechanically crushing, extraction, filtration and enrichment of minor compounds. That means these are actually the pre-treatment that we have to give to the sample. That means sampling. We have seen the chapter in unit first, sampling. That means what type of sample or how much sample we have to take, then how to crush mechanically or any other kind, then if that sample may be present along with some other material, that we have to extract from that material into separate, then filter it, and then that compound we can use, or you can say sample we can use for the separation purpose. The sample then dissolve in the proper solvent. That means we have to first check the solubility or miscibility in particular solvent. Then that sample we can use for the analysis. The solvent should be non-polar and volatile as far as possible. See, because our stationary phase may be the polar, so our solvent should be non-polar and must volatile, right? So these are the criteria to follow while preparing the sample for HPTLC. So third steps will be the application of sample on HPTLC plate. That means how to apply sample on HPTLC plate. That we are going to see now. For application of sample on plate, the automatic application device is used while using graduated capillaries. See, in ordinary TLC plate, we are using the capillaries for applying the sample, but in HPTLC plate, here we are using the automated machine, or you can say device, to spotting the sample. Usually, application of 0.5 to 5 microliters volume for HPTLC is recommended. Actually, up to 0.5 to 5 microliter, we can spot the sample on HPTLC plate. The size of the stationary zone of spot, or we can say band, will be minimum up to 0.5 to 1 mm. Stationary zone of spot. That spot should be zero point 0.5 to 1 mm only, either spot or band. Spot means circular and band will be the rectangular in shape. See, that will be the actually 0.5 to 1 mm in size of that stationary space of the zone. The concentration range of sample 0.1 to 1 microgram per liter. See, that means very dilute sample solution we can use into this application of sample on HPTLC plate. The various techniques of sample applications are actually as a spot or as a band. See last one, as a spot or as a band. Spot means what? Circular in nature, and as a band that will be the in rectangular form. By these two technique will be used or applicable to the sample application in HPTLC plate, or okay say on HPTLC plate. So for applying samples as a spot, a nanomat machine is used, and for band application, linomat instrument is used. You have to always keep in mind for what? When we give the spot, that means circular, for that purpose we have to use nanomat machine, and for as a band application we can use linomat machine, or you can say instrument. The linomat instrument is the instrument which is allows sample application in narrow bands by spray on technique. Linomat, that will be the device which is allow the sample application in narrow band. Narrow, that is generally in rectangular form by spray on technique. That means it will spray on the sample on the TLC plate. Advantages of application of sample as band are, that means when we apply sample as a band, it is having four applications. See that first one, better separation because of rectangular area, equal RF values of the compounds from the sample and reference solution. Third one, response of densitometer is higher than observed from an equal volume of the same solution. And last one, large quantities of the sample can be handled for application. See, that means if see the first application, in that case the separation will be the very nice one because of the rectangular area, and we will get the equal RF values, that means standard and sample we can compare, that we will get the equal RF values of the compounds. Then response of densitometer is higher, that means when we scan that spot, separated components spot, we will get the, or we can say we can easily observe with the help of densitometer. Then large quantities of the sample, that means we can apply 20 to 40 sample on the same plate. These are the advantages of application of sample as a band. Now we will see the fourth number step, that is development, or we can say separation or mobile phase. That means by using the mobile phase, how we can develop, or we can say how we can separate the sample component. The mobile phase is called as solvent system. Choice of solvent depends on chemical properties of the analytes and sorbent layer. That means what type of sample we are going to analyze and what type of sorbent material will be used for making the supporting layer. Depending on that, we have to select or choose the solvent. Use of mobile phase containing more than 3 or 4 solvents should be avoided. That means many solvents we have to avoid while preparing the mobile phase. Laboratories equipped with complete HPTLC system, usually smaller development chambers such as twin tube chamber, that twin tube chamber having size 10 by 10 centimeter. See, this is the actually twin tube chamber. This is the saturation chamber where we can separate the component. That will be the rectangular in form. In that chamber, generally 10 to 15 ml volume of mobile phase required. Around 10 to 15 ml volume we can use into the twin tube chamber for the separation of the sample component. For use of chamber must be saturated with solvent system. That means when we pour the mobile phase into the twin tube chamber, then keep the lid on that chamber and must saturate with the solvent system. Then we have to keep the plate into that chamber. If initially tank is saturated to be development, solvent vapors soon get uniformly distributed throughout the chamber. That means when we keep the TLC plate after spotting the sample material on that TLC plate, then keep the lid, and when this saturation is completed, then the entire vapors of the solvent will get distribute uniformly throughout the chamber. That will be helpful for what, to getting better separation. When plate keep in saturated chamber, it soon get pre-loaded with solvent vapors. Then hence less solvent is required to travel a particular distance of sample, or you can say it can easily separate out the sample component. Resulting we are getting good RF values. When we do above procedure, then we will get the good RF values. Fifth number step, that will be the detection and visualization of the TSC plate. As soon as the development process is complete, the plate is removed from the chamber and dried to remove the mobile phase completely. When we remove the plate from the chamber, we have to dry completely to remove mobile phase. The zones can be located by various physical, chemical, biological, and physiological methods. See, in general TLC, we are keeping that TLC plate into the iodine chamber. That will be the physical method, or say chemical method. But in this case, there is no difficulty in detecting colored substances or colorless substances absorbing in short wavelength UV region or with intrinsic fluorescence such as riboflavin, quinine sulfate. The substance which do not have above properties, then plate is directly keep in densitometer and fluorimetric detector. See, the above properties if not present into the sample component, then we can directly keep that plate below the densitometer, or you can say fluorimetric detector. In that case, the first will be the scanning densitometer. This scanning densitometer will be used to scan that separated component that we can either see or we cannot see. For that purpose, we can scan that plate below the scanning densitometer. Densitometer instrument is used for measurement of visible UV absorbance, fluorescence or fluorescence quenching directly on the layer without resorting to scraping and elution. See, without scrapping that portion, we can directly identify the separated component by what? By absorbing UV absorbance, fluorescence or fluorescence quenching. Suppose when we pass the light or radiation source, that will sample component will be absorbed that UV light, or we can say sample component emit the particular fluorescence that we can directly observe with the help of this scanning densitometer. The measurements are usually made by reflection from the plate using single beam, double beam or single dual wavelength operation of scanning instruments. The purpose of the scanner is to convert the spot or band on the layer into chromatogram consisting of peaks similar in appearance to HPLC. That means like HPLC, we can see the chromatogram in this HPTLC also. For that purpose, we are using single beam densitometer or double beam densitometer. The position of the peaks on the recorder chart is related RF values of the spots. So first we will see the single beam densitometer. We are looking at the scanning densitometer. Into this scanning densitometer, there are two densitometer, that will be single beam densitometer and double beam densitometer. Now we will see actual working of the single beam densitometer. A detector used for HPTLC is densitometer, which is also called as scanner. That means simply this densitometer will be scan that plate, entire plate, and whatever separated component will be present on that plate, that will be recorded with the chromatogram. It is used for quantitative evaluation by recording absorbance or fluorescence. That means either that sample component absorbs UV light, or either that sample component after absorbing UV light it will emit the fluorescence that we can identify with the help of this densitometer. A single beam densitometer is designed to a single beam spectrophotometer. Generally, the single beam spectrophotometer, densitometer and spectrophotometer generally both are the around the same. The beam first fall on the plate when sample spot not present. It produces an output as a blank reading. That means when we falls the light on plate, but on that plate there is no separated component, then we will get the blank reading. That means there is no separated component, or you can say sample. But then the beam fall on separated compounds, it will produce some output signal. See, if the component may be present on the LC plate, separated component, then it will immediately show the particular output signal of that sample separated component. These two signals are the process to produce a net signal corresponding to concentration of the components in the spot. So this is the working actually a single beam densitometer. Now we will see the schematic diagram of the single beam densitometer. See that diagram. So this is the single beam densitometer schematic diagram. Now we will see each and every component of this single beam densitometer. So the first component will be here is the source. This is the radiation source, or you can say light source, UV light source. This will be the collimating lens, entrance slit, monochromator, converging lens. Here is the plate, rectangular shape plate. Here will be the detector. See, this light source will be emit UV light. That polychromatic light will be falls on this collimating lens. This collimating lens convert all light in one direction. That means in this direction it will transmit that all light which is going through this entrance slit. See, this is the entrance slit and falls on this monochromator. This monochromator, that polychromatic light will be converted into the single beam, and that single beam light will be falls on this converging lens. This converging lens will, that single beam light will be focused on a single point. See that all direction of that light will falls on this single spot, or can focus of just like our battery. That single light will be falls on a particular single point, and the plate, this is the plate, will be totally scan through that single point of light, and the sample component will be either, if present on that plate below that light, it will produce a particular output signal. But if there is no separated component observed on plate, then the instrument show the blank reading. When the reflected light of the sample component, either the fluorescence that will be falls on this detector part, that detector will be detect that light and give the characteristics, or can say net signal, and record into the recorder of that chromatogram of each and every sample component. So this is the schematic diagram of the single beam densitometer. Into the next lecture, we are going to learn the double beam densitometer. So thank you, dear students.